we know the speed at the bottom, v2, was square root of 2g h1. Actually, in this problem, I told you to just use the symbol h for h1. So maybe I'll just go back to using an h here. You should always use the symbols that are given in the problem. So I'll just use h for h1. Okay, so that's how we solve this. All right. Okay, so that's quite a bit of things right there. So to review, the first thing you did was identify all the forces, and that was good. It was good to identify all the forces. Then you thought maybe we should use Newton's second law. Now you could solve this using Newton's second law, but it takes more time and it's easier to make mistakes. So remember, when the question is asking about speed or distance, work and energy are usually your better approach. When the question is about acceleration or time, usually force Newton's second law is the best approach. So we start with this key equation, and then you have to figure out what to put on the left-hand side here. And that's why it was so important to identify the forces, so that we could see that there was no work done here. Gravity is conservative, so it didn't appear, and the normal force is perpendicular to the movement, so that didn't appear. And once we see that the energy is not changing, this is the best way to write the equation. E initial equals E final over here. E initial equals E final. And then we just start plugging in more and more detail, looking out for terms that are zero, so things can simplify for us. Yeah. So working energy. So what we were using here was this idea. Net work non-conservative is delta E. All right, and what we especially saw here is if the net work is zero, then this is the best equation to use, conservation of energy. For problem solving, we use net work equals delta E, or this. Work and energy are useful for problems about velocity and displacement. Like we saw here, Newton's second law plus kinematics is better for acceleration and time. And the other thing that we used here, this summarizes all the different types of energy that we've seen. The other thing we've seen is how to determine the work. Well, you need the component of the force that's parallel to the velocity. And again, we saw that the normal force was perpendicular to the velocity, so it didn't do any work. Okay. Now, this would be too easy to be a real exam problem, so let's complicate this a little. So let's put another block at the bottom. Okay, now let's say, so you can see now that A is going to collide with B. So you can be sure that there's going to be at least one collision problem on your exam. So we should see how to deal with collisions. So A is going to collide with B at the bottom. And now I'm going to tell you that A will collide and stick to B. So let's say they're covered with glue. So once they, well, not covered with glue or they wouldn't roll, but their sides have glue on them, so they'll stick together. All right, so now we have a new problem. Let's figure out what the speed of the combined object is going to be after they collide with each other. So we know that when A reaches the bottom, it's going at this speed, v2. But then we want to know what's the new speed going to be after these have collided with each other and stuck together. So take your time and give that a little thought and tell me if you have any ideas about what would be our general approach here. How would we get started with that?
momentum here, that means that it's going to be the same here.
Good.
And that's my net momentum, and then that's
Great. Okay, good. That sounds very good. Yeah. Now, probably the best way to set that up then is to simply say, now how do we know this is going to be a conservation of momentum problem? Basically because it's a collision. Any collision, you're probably going to use conservation of momentum. All right, so our basic equation is net momentum initial equals net momentum final. Because the momentum is conserved, that means the total initial momentum equals the final momentum. Now, I keep saying initial and final, but maybe I should say 2 and 3. Because now we're considering situations 2 and 3. Situation 2 is before the collision, and situation 3 is after the collision. Okay, let's see if I can stick with that. So, how many objects are there in situation 2 before the collision?
2.
2 objects. So that means we're going to have 2 terms over here. So for example, we're going to have the mass of object A times the velocity of object A before the collision, but we already know what that is. That's this over here, so maybe I can just go ahead and plug that in. So we already know that before the collision, object A has this velocity, root 2 gh. So this will be the momentum of object A. Here's kind of a trick question. What would be the momentum of object B before the collision?
0.
Yeah, because it's not moving before the collision. So even though there's 2 objects, one of the terms is very simple. And we know that the symbol we're using for the mass of object A in this problem is just m. So I'll just use m for the mass of object A. Now, how many objects are there going to be in situation 3, the instant after the collision?
1.
Yeah, just 1 object. So what should I write down then? And how are we going to calculate that momentum?
It should be equal to the momentum, the starting momentum.
Right, so here's our starting momentum. Now we need to write a mathematical expression for the final momentum, so that we have something on both sides of the equation. So what would be a mathematical expression we could write down for the momentum of the combined object after the collision?
The mass of A plus B times the square root of 2gh.
Okay, that's on the right track. So what's the basic formula for momentum? The basic formula is mass times velocity. All right, so what's going to be the mass of the combined object?
Mass sub A plus B.
Right. Now what's the symbol that we're using for the mass of object A in this problem?
M.
And what's the symbol that we're using for the mass of object B in the problem?
M.
Also M. So then what would be the combined mass?
2m.
2m. Good. So you're right that in general it would be m sub A plus m sub B. In this particular case, we know that's going to be 2m. Okay, good. So that would give us 2m for that mass. By the way, notice that in this problem I didn't give you any numbers. I just gave you variables, but that's pretty typical for the problems you're likely to see on the exam. In fact, you're probably more likely to see variables than numbers. And when you have that, it's important to use the variables that match what you're given in the problem. So here we were given these symbols for the masses. All right, so the combined mass would be 2m. And then we have to know what the speed is going to be. All right, now it's actually, we can't assume that this speed is the same as this speed. This was the speed the instant before, right? So this is what the question is asking us for, right? The question is asking for the speed after the collision, so we can just call that v3. That's the speed in that new situation. And we're not going to plug in an expression for that. That's what we're trying to solve for. Now what?
Solve for v3.
Okay.
And then use that to solve for the momentum. Well,
what was the question?
We're solving for v3.
That's right. So in fact, once we have v3, we're done. We've already written our expressions for the momentum. And the reason we did that was to solve for v3. Okay, so let's go ahead and do that algebraically.
Okay, so then it's divided by 2m.
Good. So the m's cancel again. Good.
So it's square root of 2gh over 2.
Yeah, that's good. So again, we can cancel the m's. And we get this as our v3. And that's really what the question was asking us for. So we're done. So that new speed would be root 2gh over 2. Okay. So to review how we did this here, we saw that this was a collision problem, which should indicate momentum. Collision, we use momentum. A good way to start is to write net momentum in one position equals net momentum in the other position. Well, when we worked through this before, we did this with a lot of pictures, of the two different things and everything. It might be good to do that problem this way as well, but for time constraints on the exam, you might be better off just writing down this equation.